Look, 5 red data points appear on a grid, one by one, the raw material of every line-fitting problem. A blue optimal line slices through the best single summary of these scattered points. From each point to the line, orange squares bloom. This is the geometry of least squares. Textbooks present least squares as this intimidating formula memorize. Plug in numbers, done. But the real insight is not algebraic, it is geometric. Points, a line, and squares. Watch the formula shatter. Quind, out of the fragments, the geometric truth emerges. Look at the largest orange square. Its area is exactly 1.00. The golden glow traces each residual square. Each square encodes the square distance from a point to the line, a geometric measurement of error. By the end, you will see why squaring errors is not arbitrary, it is geometrically inevitable. And it powers everything from neural nets to physics to finance. What makes a line the best? Let us test 3 candidates on the same 5 data points. First, a terrible fit steep slope. Wrong intercept. The gaps are enormous. Total squared error. S. A massive 19. A better attempt closer to the data, but S is still 14.75. The squares have room to compress further. Finally, the optimal line. The squares hit their minimum S equals 1.9 and cannot go lower. 3 lines, 3 error. Totals 1 clear minimum. That is the core of least squares. A 5-step roadmap. Data points, measure residuals, square them into areas, sum into total cost S, and find the minimum. Each stage has its own animated icon, a pipeline from raw data to the optimal line. Let us build it one piece at a time. 5 steps, 1 goal. The line that minimizes total squared error. Define a residual precisely. Focus on 1 point, coordinates 1, 2. A dashed line drops vertically to the blue fit line. The prediction is 2.2, so the residual is negative 0.2. In symbols, E1 equals Y1 minus A x1 plus B, that is, actual minus predicted. A residual is simply the vertical gap between a point. The total cost depends on 2 knobs, slope A and intercept B. Twist either and the line moves squares resize. We write S of a comma B equals the sum of y minus x minus b all squared. The square makes every term positive. Our goal, find the values of a and b that make S of a, b as small as possible. Every combination of a and b is a point on this surface. Height equals total squared error. S a smooth parabolic bowl. Colored contour rings, green near the minimum, yellow in between, orange farther out. The camera orbits slowly around the bowl. A golden marker slides downhill following steepest descent toward the glowing green minimum at the very bottom. The live inset shows the line updating as the marker descends. Finding the best line means finding this lowest point. How do we find the bottom of the bowl? Calculus. Start simple. Here is y equals x squared. A dot starts at x equals 2 steep slope of 4. It slides downhill as the slope drops, reaching 0 exactly at the minimum. In 2 dimensions, both partial derivatives must be 0, 1. For slope A, 1 for intercept B. The cost function is s equals sum of y minus a x plus b, all squared. On the left, a miniature 3D bowl with the minimum. Set the partial with respect to it to 0, and the partial with respect to b to 0. 2 equations for a and b. Solve them, and we have the optimal line. Least squares is everywhere. Machine learning the loss function behind regression. Curve-fitting polynomials and exponentials. Physics labs trend lines through experimental data. Gradient descent rolling downhill when there is no formula. 4 domains, 1 geometric idea. Least squares connects them all. Geometry plus calculus equals least squares, 1 picture. The whole argument. One final comparison. What if we used absolute values instead of squares? L2 on the left, L1 on the right. Orange squares, total error 1.90. Purple diamonds, total absolute error 2.40. Different measures for different needs. Which one fits your data?